So hello everybody. So today we continue to talk about the AC systems. First of all, I remember that last week we stopped at the tutorial example 2 on the single phase AC systems. And today we have to continue to finish this tutorial examples first. Then we move to the three-phase circuit systems. In the for the tutorial question 2. Actually, it has three parts. The first part that given that the loading informations and loading including the loading powers, loading power factors, and the voltage cross loadings. Given that the supply cables informations, which can be obtained from the tables, and then to find out the required supply voltage. And the second part is that how to making the power corrections. So actually, the power correction is that to making the reactive powers be compensated with the other parts. For example, if you have an inductive load, which usually has inductive reactive powers, we can connect to the system's capacitive reactive powers, so that the reactive powers the total reactive powers be small or be zero. The third part is that they are supposed that if the loading impedance be zero, that means there is a short circuit occurred at the machine terminals. Then it just includes the internal impedance of the machines and the cable impedance. Then there is a so-called short circuit occurred. In that case, the source impedance is very important, which limits the short circuit currents. Okay, for the first part, actually we explained in details last week. Generally speaking, that the source voltage. Remember, the source voltage equal to the load voltage plus cable voltage drop. So this is the basic issues. Pay attention to voltage, phase angle, each voltage phase angles. The source current cable current and current to the load is the same. Okay. So cable voltage drop equal to cable length times current times cable value Okay, so anyway, so to make the things be more clear, then here, instead of the formulas, I would like to write down some things here. The first, the source voltage. In distribution systems, we have the source, we have the cable, we have the load. Okay, so the source voltage equal to load voltage plus the cable voltage drops. Yes, so pay attention to each voltage phase angles. Okay. The second point is that the source currents, the uncable currents, and the current to the load are the same, okay, in the systems. The third point is that the cable voltage drop equal to the cable length plus the current, okay, times the current times the cable table values that the voltage drop per ampere per meter in the tables given. Okay, with this in mind, that you can deal with any kind of the power distribution systems. Okay. Okay. Another point is that the current is always in phase with the resistive voltage drops. So in the systems, the cable has a resistance, the load has a resistance, whatever components has a resistance. So there is so-called resistive voltage drops. The voltage drop cross the resistive, right? Resistance. Resistive voltage drops. In that case, the current always in phase with the resistive voltage drops. Okay. So and you should know how to find out the impedance angles, how to find out the phase angles. Okay, the phase angles, right? The difference between the phase angles of voltage current comes from impedance angles. Okay, so this is the example, a tutorial example to the first part of it, and we have summaries here. So pay attention to the summaries. Summary here. Okay, so you may have different. Okay, you may have different approaches to achieve the answers, but the principles is written, right? The principle is written here, Remember it? Okay. So this is the first part of it. Okay, we do not explain of it again. And now we go ahead to see the second part, that is about the power corrections. Okay, the second part is the power corrections. The power, as you know, the power factor is the cosine impedance angle, right? Impedance angle. System impedance angle. So for a given load, okay, so it has impedance. Okay. Sorry. Load power factor is cosine of the load impedance angle. Total system power factor is the cosine of the total system impedance. Okay. Here we have to, right? Sometimes we talking about power factor correction. That means the systematic, right, power factor issues. For each loadings, it has, right, impedance. So the load itself has the power factors. So generally, most of the rotary machine, rotor machine is inductive one. So it has lagging power factors. However, so this making the current on the distribution line be a little bit larger than the required currents. So to making the current on the distribution line be smaller, we have to making the system's power factor be close to 1. So then how to making of it? So generally we in connection in parallel connections to the machine with a capacitor. So connect a capacitor in parallel with the machine. Right figures can improve the power factors. So the machine's power factor, so determined by the machine's impedance. The system power factor determined by the total impedance of these two parts. So the total impedance, admittance that is the 1 over impedance. So admittance is the 1 over impedance. That's the admittance. So now we're looking at the systems, right? Total admittance. Total admittance is the machine's admittance, which is the inductive one, plus the capacitors. If we have a capacitor in parallel with it, so which the machines has a resistance, machines has a reactance, the inductive reactance, and for the capacitors, it has a capacitive reactance. So to make the power factor be 1, that means we making the machines reactive power part be 1, reactive power be 1. So that's the meaning reactive power be 1. So imaginary parts be 1, imaginary parts be 1. So making the power factor be 1, making these parts be 0. Only the real parts be here. Reactive power be 0. So that means making the power factor be 1, it should be that the reactive powers, reactive, reactive power be 0. That means reactive, reactive power be 0 means the reactance, total reactance be 0. With 0. So one can quickly find out that the required capacitive reactance. So this capacitive reactance can be calculated, and the required capacitors can be estimated. So here just showing you the principles how to make a power factor corrections, which in the next semesters when you not in the next year when you learn about power distribution, you will learn more about power factor corrections. There we have more approaches to achieve the power corrections. This is the second part. The third part actually is showing you that the third part means that if the machine's impedance be 0, that means if there is a short circuit occurred at the machine terminals, then the system voltage be consumed by the cable and the internal impedance of the machine itself. Generally, the cable impedance is very small, and the internal impedance of the machine, internal impedance of the source also is very small. Given that for this case, the cable impedance, which in the first parts has been estimated, which is very small with 50 meters long, very small, which has a very, very large impedance angles, almost 70 degrees. So the cable impedance from the tables can be found out, the total impedance 0.0135 ohms. And the source internal impedance, which the question is given, and about 0.1 ohm, 60 degrees. Compare that 0.013 ohms. This 0.1 ohms. So the cable impedance very smaller than the very smaller than the internal impedance. Okay, the internal source impedance. So the total reactance of the systems and the short circuit case, the total resistance of the systems and the short circuit case, right, can be estimated. Therefore, the total impedance of the system and short circuit case, which including both the cables and internal impedance of the machine, of the source. So we can determine that the total impedance determine the total impedance angles, which also is the phase angles between phase angle difference between the voltage, source voltage and source currents. Okay. So with this right informations, one can quickly estimate at the moment short circuit the peak current with the formulas that we got in lectures. Okay, so you will find that the peak currents at the moment, right, short circuit will be very large than the normal current because the small impedance of the cable and the small impedance of the source itself. Because that we have a detailed procedures, right, writing in the tutorial examples, so you can take a look in detail, right, step by step by yourselves after the tutorials. Okay, so anyway, so since the single phase, right, AC, its difference to the DC system is that we have taken account that the impedance angles, the current phase angles, that the voltage phase angles. So there is angle issues. So pair-attached angles, if you have a good understanding about the complex number forms or polar forms, I think you have the basic principles of the calculation analysis is similar to that in the DC systems. Just pay attention to the complex numbers, pay attention to the polar forms. Okay, that a little bit complicated in terms of mathematical calculations. Okay, so now we will move on to study about the three-phase systems. So we come to the three-phase systems. So the three-phase systems, the basic principles also very similar to that of the single-phase AC, unless that here we involve three single-phase sources in a systems. So we have to pay attention to that the difference between three single-phase in the three-phase systems. Okay. So we have the so-called balanced systems and unbalanced systems. The example one is the balanced systems. Okay. Okay. So balanced system means that a three single-phase system, right? And they have the same right. Okay. they have the same voltage current and impedance except the phase angles. So they have 120 degrees in terms of phase angles difference in the source voltage. Okay, the others are the same. So that's the balanced systems. Therefore, for the balanced systems, we just need to analyze the per phase issues. Then the other two phase has the same values with that. We analyzed, unless that their phase angles are different. Now, looking at example 1, which is a resistive, right? Three-phase systems, balanced systems. The question 1, so you are required to design a three-phase 18 kilowatt instantaneous water heater. Find the resistors of the three resistors if they are connected in 1 star, 2 delta without star delta transformation, and 3 delta with delta star transformation. So this is very simple, right? Three-phase systems, because it is a resistor, right? The resistive, right, load. First, we should try to understanding the meanings of the information given here. So given that the three-phase power 18 kilowatt. So the 18 kilowatt here is three-phase total powers. Three-phase total powers, real powers. The unit is kilowatt. That's the real powers. So the total real powers is 18 kilowatt, three-phase. Now, assuming that in the three-phase systems, the 9 voltage here for Hong Kong is 9 voltage in three-phase systems is 380 volts. So the 9 voltage is 380 volts. The 9 current is I. And we suppose we have 3 pure resistors are used. Then the power factor will be 1. Okay, so remember the power factor equal to 1 for resistor. This is very important. Then the real powers, here some students may confused, right? So the real powers, as you know, for three-phase systems, balanced three-phase systems, using the 9 voltage, 9 current, rule 3 is enough. Is enough, right? So 9 voltage, 9 current, and rule 3, the power factor, which is the true powers, real powers. So here, giving that real powers is 18 kilowatt. 18 kilowatt. Look that, sorry. This also can be right into the 3 times the phase voltage and the phase current. For resistors, the power factor equal to 1. So resistor power factor equal to 1, and real powers, which is 9 voltage, 9 current, and root 3, or 3 times the phase voltage, phase currents. The same. Here we use the 9 values. So given the powers, we can find out the 9 currents. 9 currents. Okay, so 9 voltage, 9 currents. Now, okay, for a star connection, the right, so the resistance per phase equal to the voltage, phase voltage over the phase currents. Okay, so in the star connection, the phase voltage here is the 9 voltage over √3. And the phase current equal to 9 currents. Equal to 9 voltage. So because some students always confused with these points or forget these points, okay, 9 voltage over √3 and phase current equal to 9 current for star connection. Okay, for star connection, it is easy to find that the phase voltage equal to 9 voltage over √3 and the phase current equal to 9 current for the star connections. So therefore, we can easily find out the per star equivalent resistance required is 8.07 ohms. Now, we're looking at the direct connections. For direct connections resistor without using the star-star direct connections, the phase voltage equal to 9 voltage. And the phase current equal to 9 current over √3 for delta connection. We are talking balance systems. We are talking balance. Example 1 is balance systems. Remember this one. So the phase voltage equal to 9 voltage, and then the phase current equal to 9 current over √3 for the delta connections. So here, so for the delta, right, equivalent resistance required if it is delta connection. Then it is the phase voltage over the 9 phase currents. But the phase current voltage, that is the 9 voltage, the phase current, that's 9 current over √3, which has been obtained right in the first slide of this example. So we bring in that we got that, So the delta equivalent resistance required is 24.2 ohms, which is 3 times of the star connections. So in direct connection, the resistance is bigger. In the star connection, resistance is smaller. Their total powers is the same. The source is the same. You found that difference? Now, so for the direct connection resistors using the star-delta transformation, so we suppose that for equivalent star connection for the direct connection, and we learned in the lectures that we have so-called formulas. So for a star connection, so if we have the star resistance R red, R yellow, R blue given, that the direct connections, the resistance between the red yellow, so between red and yellow, that is red plus yellow plus red times yellow over right, the resistance blue. So here for balance systems, red, yellow, blue the same, which is the star connection values RS. So the direct connections resistance can be easily found out, which is the 3 times. Simply speaking, the delta 3 times the star. for balance systems. Okay, for balance systems, the delta equivalent per phase values equal 3 times the star per phase values. Okay, star per phase values, delta per phase values. Okay, the 3 times difference. That's the key issues we would like to tell you in example 1. The calculation in example 1 very simple because we would like to emphasize on the 3-phase balance system concepts rather than the calculations. That's example 1. Now example 2. Okay, so which right-hand systems be unbalanced? So unbalanced 3-phase systems which have the same source, right? Okay, same source, but the 3 loadings is different. Okay, that's looking at these examples which are very typical to see how to analyze the unbalanced 3-phase systems. Now here, given that a star-connected 3-phase supplier with a voltage 346 is supplying the 3 single-phase loads, each rating at 200 volts, a 820-watt toaster is connected to the red phase. A hair dryer of 1200 watt is connected to the yellow phase, and lastly, a 100-watt tungsten filament lamps connected to the blue phase. So here, the 300 is the 9 voltage. Remember, 9 voltage. In 3-phase system, we're talking about 9 voltage, right? Okay. So here, 200 volts. Do not confuse rating voltage of so here, so the 200 volts is the rating voltage of single phase load. Okay, so it is not right. The 9 voltage, it is not right. It is just is the rating voltage of the single phase load. Single phase load. So you have to deal with right this as a single phase voltage. And the 820 watt, so 1200 watt and 100 watts are the real powers for the 3 single phase loads. Okay, looking at these 3 single phase loads, they are all resistive loads. That means their power factors are all 1. Okay, so the neutral conductor at the source end is disconnected accidentally. That means originally it is a 3-phase 4-wire star-star connections. But due to the accident, so the neutral line is broken. Now, the system becomes a 3-phase 3-wire star-star connections. Now, calculate the 9 currents. State all the assumptions clearly. Now, we're using the diagrams showing you that we have a 3-phase systems. It has 9 to 9 voltage, 346 volts. Okay, but it has a phase voltage 200 volts and the source side. Okay. Now, looking at the user side, we have 3 resistors. Okay, the first one rating 800 watts. The second one rating 1200 watts. The third one rating 100 watts. If their rating voltage be 200 volts. Now, the neutral line broken. So the system becomes a 3-phase star 3-wire systems. Okay, so making the systems, okay, the voltage to the load no longer due to the neutral line breaking. Okay, so remember that, okay, if it is a 3-phase star 4-wire systems, then each load here is getting 200 volts. However, so due to the neutral line brokens, the voltage to each load is no longer 200 volts. So that's the key issues. Now, before doing the analysis of the systems, we have to, because we do not know the per phase voltage, we do not know the voltage to each of load. So we learned in the lecture that, okay, for a star 3-wire systems, okay, it is better to transfer it into a delta connection. Then we can do the calculation easily. Now, we first to find out the 3 resistors. For the toasters, its rating powers 820 watt with rating voltage 200 volts. So the resistance of the toasters can be estimated with their rating voltage and the powers. Okay, resistors equal to rating voltage square over rating power Okay, remember, the resistance is the rating voltage square over the rating power for resistors. Okay, for resistors. So rating voltage square over rating powers. So for the red, yellow, blue, we can estimate their equivalent resistance. Then, if we using the star delta transformation formulas, that we can get the delta connections 3 resistors. So the resistance between the red and yellow can be estimated, and between the blue and the red can be estimated, and between the yellow and blue can be estimated using the formulas, given that the red, yellow, blue estimated here. So we do not recalculate it, just showing in the procedures. So with the delta equivalent resistance calculated, now the system becomes a 3-wire star delta connections. 3-wire star delta connections, as we shown here. Although the loading is resistive 1, but the voltage red, yellow, blue phase still have the phase angle difference. Okay, so now, so with the direct connections, for direct connections, the phase voltage equal to the line voltage. So for in the direct connections, the phase voltage equal to line voltage. So the phase currents, red-yellow phase current, red-yellow phase current is red-yellow line voltage over red-yellow resistance. And red-yellow line voltage is this voltage, right? Is this voltage, red-yellow line voltage. So it is given that values is 346 volts, not 380 volts, right? So the red-yellow voltage is these values. Okay, so red-yellow voltage is in this direction, which is leading the red voltage by 30 degrees. Okay, generally we say the red currents equal to 200 volts with angle 0 degree. Okay, we define the red phase voltage be 200 volts with the angle 0 degree, angle 0. Okay, then the line voltage between red and yellow is 30 degrees. So this is the voltage, this is the resistance. So we got the phase current, red-yellow phase current. We write it into Poynter form and Compson-Lambert forms. Okay, we can calculate the phase current of the red-yellow phase, pay attention to the phase angle here of voltage. Okay, the impedance angle is 0 here. Okay, in practice, maybe you have impedance angles also here. So we can go to the phase currents, so Poynter forms and Compson-Lambert forms. Similarly, we can calculate the phase current between the phase blue and red, which write into the Poynter forms and Compson-Lambert forms. We can write get the yellow-blue phase currents, okay, which is the Poynter forms and Compson-Lambert forms. So finally, here, that with the phase current here, delta phase current here, we have to find out the line current here, So the red line currents, look at here, red line currents is the red-yellow phase current minus the blue-red phase current according to the Kirchhoff current law and these points. Okay, so the red line currents equal to the red-yellow phase currents minus the blue-red phase currents. Remember, current flows from the assumed high potential point to the assumed low potential points. Okay, the voltage is point from the low potential point to the high potential point assumed. Okay. So you can, using the complex number of forms, easily got the red 9 currents. So red 9 currents is the red yellow complex number of forms and blue red complex number of forms. This one minus this one. Okay, the real parts minus together and the reactive parts minus together. You can gauge the complex number of forms of the red 9 currents. Furthermore, you can convert it into the Poynter forms of the 9 currents. So red 9 currents, Poynter form, complex number of forms. Similarly, you can find out the yellow 9 currents, which is the yellow-blue phase minus the red-yellow phase, which is indicated in the diagrams here. Looking at diagrams, the yellow currents in here, which is the yellow-blue minus the red-yellow here. And similarly, the blue 9 currents, look at here, blue 9 currents, we suppose in this direction, blue 9 currents, which is in here, which is the blue-red out minus the yellow-blue in. Minus yellow-blue in. So you can write into the both complex number forms and the Poynter forms. So these Poynter forms, the phase angles of the current red 9, phase angles of the yellow 9, phase angles of the blue 9. They are no longer 120 degrees difference, no longer, because they are unbalanced. Theoretically, if they are balanced, so 0 degree, 0 degree, 100 minus 120 plus 120, but unbalanced. Unbalanced. So you can draw the phasor diagrams based on these values. So with the Poynter forms given here, you can draw the phasor diagram with these Poynter forms easily because the angles are given here. You suppose the 0 degree directions and suppose, then you can draw the phasor diagram easily. That's example 2. So the example 3, which is the balance systems again. But here, so showing you for balanced 3-phase systems, if we know the ratings of 3 balance systems, how to find out their equivalent impedance of the systems. So given here, this is a balanced with inductive 3-phase load. So 3-phase load, right? So how to determine their equivalent impedance, per phase equivalent impedance? So this is a balanced 3-phase system with an inductive 3-phase load, So it is a 3-phase load. It involves 3 single-phase loading, but identical. How to determine the per phase equivalent impedance is the key issues for the three-phase balanced inductive load. Here, given that we have a three-phase, right, systems, delta connected source, which has 346 volts delta connected source, is supplying a balanced load of 300 kVA and 200 kilowatt, and a capacitor back of 60 kVAr through a cable of impedance of 0.01 ohms, 70 degrees, okay, impedance angles. Find out line currents and their phase angles. So we're looking at the drawings here. Sorry, because it is a direct connection that it is a balanced systems. We just need to analyze the per phase issues. So we need to find out the per phase impedance of the load, per phase impedance. Okay, so to solve these questions, we needed to find out the per phase impedance of the load, the cable, and the capacitors. Then we have the three impedance, okay, connected together in a single phase. We can do the single phase calculation because it is balanced one. Okay, it's balanced one. Okay, so since the source is 346 direct connected and the loads are in balance, this circuit can be analyzed by using a single phase sequence circuit. Assuming both the load and the capacitors are star connected. Yeah, star connected. So load per phase, now load per phase, star phase, for star phase. Okay, so for the load per phase impedance, now look at here, which give you the hints. Okay, so the per phase impedance of the star connection is the 9 voltage square over the total powers equal to 9 voltage square over total three-phase power Okay, so for the three-phase loadings, per star phase impedance equal to the 9 voltage square over the total three-phase powers. Y per star impedance equal to, for example, phase voltage over phase current. Equal to the phase square. Square over power phase. Okay, for star connection. Okay, this is the power phase power. 3 times the phase square over 3 times phase powers equal to, okay, 9 square over okay. So first, the per star phase impedance. Per star phase impedance equal to the per star phase voltage over the per star phase currents equal to the, okay, per star phase voltage square over the per phase powers. Now equal to the 3 times, okay, per star phase voltage square over 3 times per phase powers. So you know root of 3 phase voltage is the 9 voltage, right? So 3 times, right, phase voltage square, that is the 9 voltage square. And 3 times a single phase power, that is, okay, phase power. And that's the total of 3 phase powers. That's the meaning of it. Okay? That's the meaning of it. Okay? So that's why we have the phase, star phase, star phase impedance equal to V, okay, 9 square over the total. Okay, that's the meaning of it. So load per phase impedance can be estimated like this. Okay, so the power factors is the true power factors is the P raise. So therefore, the impedance per star, okay, can be found out. Per star phase can be found out 0.4 ohms. That the impedance angles from the power factors can be, okay, determined. Similarly, the capacitors can be from their total powers, which reactive 1 and 9 voltage, be determined per, okay, per star phase. So okay, so the example 1 is, so example 3 we stop here today because we need more times to talk about this one. So we can continue finish this one, okay, next week or 8. Okay, so anyway, so please take some time to review the, okay, 3-phase lecture notes so that you have a clear understanding of the difference between the 3-phase and the single phase. So thank you all for attending today's tutorial sessions.